Hello. Tonight's video, we're going to look at discrete time Fourier series properties. I'm going to show two examples of how we use Fourier series properties to relate the Fourier series in the time or the signal in the time domain x of n to the Fourier series a sub k in the frequency domain. And we're going to use the same signal in the discrete time Fourier series example, the example of computing the Fourier series. So this is a square wave signal. There's 1 for 3 samples and then 0 for 3 samples after that, and repeats periodically. Right? We can actually sort of highlight one period here. If I come in with a green pen, I can say, well, I can pick actually any period I want. But oops, that's not very green. Let's try this again. So right, we get this period here from say -2 to 3. It's pulling out one period of the signal. And this is n equals 6. I can take any period of 6 consecutive samples I want. And when I do that, we found in that example, the equation for a of k is 1/6 plus 1/3 cosine of pi over 3k. And if I plug in the values of k to evaluate this, I can go through and say, well, when k equals 0, I get a half. K equals plus or minus 1, I get a third. Plus or minus 2, I get 0. And when k equals 3, I get minus 1/6. So those are the values of the Fourier series for this this signal here. What we're going to look at now is look at what happens when I change those values, or when I change the Fourier series. So the first example I'm going to show is an example of using the modulation property. Let's open up a new page to do that on. And so we're going to say, well, what if I define a new signal? I'll have a new signal y of n, and we say this signal corresponds to the Fourier series b of k. And remember, this is not an equal sign, as we discussed before. This means that there's a correspondence between these two things, that this is the signal in the time domain, this is its representation in Fourier series. Right? Another way of saying this is also saying that the Fourier analysis and synthesis equations hold. So this is saying that if I take the sum as k goes from 0 to n minus 1 of b sub k e to the j omega naught, well, that's the fundamental frequency, times k times n, I'll get back this signal. I'm going to say, well, what if I choose b of k to be the same a of k I had on the previous page, times e to the minus j, 2 pi by 6 times k times 2. Okay, so I'm going to take the Fourier series coefficients on the previous page, and for each value of k, I'm going to multiply it by this complex number and get b of k. The question is, what is y of n? What do I get for the time signal? Equivalently, what is the effect if I do this to the Fourier series, then use my synthesis equation, which is like a recipe for making y of n? What ends up with y of n? Well, I could plug all the values in, each 1k at a time, and get these complex numbers and plug them into this sum and turn the crank and grind away. But the whole point of Fourier series properties is they let you be a smart and lazy engineer and not have to do all that. Because if you look on your favorite Fourier properties table, you'll see something that looks like this, that says the shifting property of the Fourier series says if I shift in time by m samples, it's equivalent to taking the Fourier series and multiplying by e to the minus j omega naught times k times m. So basically, shifting in time corresponds to multiplying by this complex exponential in the Fourier series. And if I start comparing these now, sorry about that, carried away with the mouse. Let's hide this too. Apologies for the technical difficulties tonight. If I start comparing these two right here, then I see a lot of similarity. I say, basically, this is the property I've used. By multiplying by this exponential, I've shifted in time. I just need to work out how much. And I can do that by sort of compare. The next step would be to, if it's not immediately obvious to you, is to compare. I need to put that recording icon out of the way over here. Is to compare the exponents to figure out what the shift of m is. So on one side I have e to the minus j 2 pi by 6 times k times 2. And over here, I'm looking to compare e to the minus j, omega naught, k, and m. So I'm working this out to figure out what m is. And if I do that, I can compare terms pretty easily. I can say, well, I've got a k on both sides, so those cancel out. This is omega naught, right? Because I had n equals 6, so omega naught is 2 pi by 6. So I can say, well, these terms cancel and the minus j's cancel, so I'm left with this term in the exponent gives me m equals 2. And this one was pretty easy. I wanted to start with the basic one for you. Sometimes it's trickier. If this has been, if this had been multiplied through, this might have been something like 2 pi over 3, and you'd have to divide out the m naught to make everything work. But the main idea is to set whatever exponent you have, if you have the shifting property, equal to this one, and then massage things around until you get an m. Figure out how to write it in this form, that I get omega naught times k times some m. So this tells me right here that the signal was shifted or delayed by m equals 2. So that says, right, based on that I can say that y of n would be equal to x of n. We'll hit the right margin of the page here. Let me slide over a bit. Would be equal to x of n minus 2. So I can go back to that get this page recentered. If I go back and look at my previous page, I can just take this periodic signal and shift it to the right by 2 samples, because I know that's what x of n minus 2 is. So if I'm going to sketch that, I can make a sketch now of y of n. Let me slide the page up to make it a little easier to draw on my tablet. Now I can say y of n. Well, I have the equation already. So if I draw that out, what that looks like, it says, well, instead of starting at minus 1, I've moved it over 2 samples to the right. So I have the same square wave here. But instead, if I shift it 2 samples to the right, the indices on the time domain should be like this. So it's still height 1, but it samples 1, 2, and 3, then 4, 5, 6 at 0, 7, 8, 9, it's 1 again, and back here going to the left at 0, minus 1, minus 2, and then it's 1 for a few samples going back this way. So this is minus 3, minus 4, and so on. So it has the same basic shape, it's just shifted in time. Another important thing to note is that using the shifting property did not change the period of the signal. This is still periodic every 6 samples, right? If I go from 1 to 7, 2 to 8, 3 to 9, I have the same values of the signal, but so using the shift property doesn't change the period when I'm working with Fourier series. Okay, so there's the first example. That's how, showing an example of I do something in K and work out what the equivalent effect in the time domain is. The second example I want to do tonight, let's make a new page. So this would be example 2. Is to work in the other direction, to show you if I have a different time signal, how instead of going through the whole process of plugging into the sum and evaluating like I did last time, I can use the Fourier series I already know and properties to find the Fourier series of the new signal directly from the old one. So instead of going through all those manipulations, I can start again. And the signal I'm going to work with is not very different. I'm going to say, let's call this signal z of n. And I'm going to assume it has a Fourier series corresponding to, we'll call it c sub k. And this new signal, I'm just going to change the old one a little bit. In fact, I'm going to show you two ways to do this. I'm going to say, what if instead of the square wave I had before, I had one that was positive and minus, going in plus and minus direction. So it's still 1 from minus 1, 0, and 1, but then the next three samples, it's minus 1. So 2, 3, 4, it goes to minus 1. And then 5, 6, and 7, it goes back up again. This is minus 2, minus 3, minus 4, up, but see, I'm making the wrong signal now. Oops, I'm going to erase that. Sorry about that. So these ones should not be 0. Clean this up a bit. These ones here should be the negative signal. Okay, so make them the signal that instead of being 0, it goes plus 1, minus 1 for 3 samples at a time. So if I had to find the Fourier series of this, I could just go ahead and plug into the sum, evaluate it, try to combine exponentials to make sinusoids or cosines. But I can also be smart and lazy and use Fourier properties and figure out if I can write z of n in terms of the x of n where I already know the coefficients, I can then use the properties. There's actually two ways I could do this. I'll show you that each of them work and each of them gives me the right answer. So the first one, we could say, well, I can think of z of n, I can say z of n is equal to 2 times x of n minus 1. If I go back a couple pages, right, if I take this signal and scale everything up by 2, I'll have a pulse that's 2, then 0, then 2, then 0. If I subtract a DC value of 1 everywhere, it will then be either 1 or minus 1 everywhere. Right, so this equation works, and that says, well, I can say if this works in the time, we know that Fourier series transform is linear. So in terms of correspondence, this is telling me that C of k is going to equal to 2 times the Fourier coefficients of A of k, right? Because this is linearity, minus, well, I still need to find the Fourier series. Undo that, that was a mess. The Fourier series of what's the Fourier series for a constant 1? Well, that turns out to be pretty easy. If I have a 1 on this side, its Fourier series is just an impulse. We won't go through that now. In fact, that's an example in the book. But the constant signal 1 is a periodic signal. If you plug it in, you can show its Fourier series is delta of k. And that makes sense because we've said the k equals 0 term is the DC term. And so it makes sense that a DC signal has a Fourier series that only consists of a DC term. So if I bring this down further here, if I bring this over, then that's telling me that C of k is going to be 2 times the equation I had before. So 1/6 plus 1/3 cosine of pi by 3 k, that whole thing, one more parenthesis, minus delta of k. So it means I subtract 1 from the k equals 0 value. So that is much more simple than going through all the sums and everything. So that's the payoff to mastering the Fourier series properties, is I get a new signal. If I can figure out how to build it out of signals I already know the Fourier series for, like constants and like the square wave I already have, I can quickly find the answer. And I can go through now and plug these in if I need to. Let me scroll up the page a bit. So I can say this is, just using what I had before, I'd say, well, it's now 2 times a half minus 1. This is for the k equals 0 term. Well, that term becomes 0, right? 2 times a half is 1, minus 1 is 0. I'll have 2 times a third, and then the delta of k term is 0 here. So I can, just to be very redundant, write that in. So I'll have 2/3 when k equals plus or minus 1. I'll still have 2 times 0 minus 0, so I'll still have 0 when k equals plus or minus 2, we're still hitting the bottom of the page here. Let's scroll up. And then instead of minus a sixth, I'll have 2 times minus 1/6 minus 0. So I have minus a third for k equals 3 or plus or minus 3. So there are the values. I could go make a sketch of this if I needed to. But again, it's much simpler than evaluating the Fourier series. I can get it in equation form, or I can plug in 6 values of k, because I have the same period in the Fourier series as I do in the time domain, and get these values. The other thing that makes sense about our answer, sort of as a sanity check, is this new signal, I get 0 for the k equals 0 term, which is the DC term, and that makes sense if I go back up here and look at my signal again. Right? This signal is equally balanced, positive and negative. Its DC is 0. So it makes sense that by changing the signal to get this, I get 0 for DC. So there's one way to find it. I promised you 2, so let me show you the second one here. Make a new page. The other way I could make this signal is by, if I look at the time domain, again, I'm using the same square wave example I've already seen. I say, well, another way I could make z of n, rather than the scaling thing, is I could say, well, I already have the right value for the first 3 values. And what if I take it by delay it by 3 samples and move it over? Right? I can sketch this in the time domain, and I'd still get that same positive-negative square wave. Because I could say I could make it out of the positive block of 3 samples for this, and then the next 3 samples I shift it over by 3 and subtract it, and it will give me this. Well, again, using the Fourier properties in linearity, I say, well, this is telling me that I get the Fourier series for x of n minus the Fourier series of this, of the delayed version. Wrong value again. I get the Fourier series, so I use that as an abbreviation, saying I need to find the Fourier series of x of n minus 3. But again, here our razor-sharp knowledge of Fourier series properties help us, because we say, well, I know from the first example we saw here, if I delay in time, it's like taking the Fourier series and multiplying it by e to the minus j omega naught k times the amount of the delay, which was m in that example I showed you earlier, which would be 3 here. So I say the new signal, the new Fourier series, is the same as the old one minus a sub k times this. And if we want to simplify that sum, we can pull the a sub k out of both terms, and I get 1 minus e to the minus j. Omega naught we can plug in, we found earlier, is pi by 3 times k times that delay of 3. Well, this will be a sub k 1 minus 1 to the k. Oh, I combined a couple steps there. I should explain. Let me use my blue color here to highlight a little bit. If I combine things in this exponent here, I'll get e to the minus j. I put the 2 3's together, and they cancel out, and I'm left with this. And then I can say, well, this piece here, e to the minus j, is a minus 1. So I can use properties of exponents to say that's equal to minus 1 to the k. So that's how I got from here to here in one quick step. Breaking that down for you. And then if I look at this, here's where the simplifying property comes in. If I look at this, when k is even, minus 1 to an even power will be 1. So I'll have 1 minus 1, and this is 0. So what this is saying is I get a sub k, and then for odd values of k, this will be a negative 1. So 1 minus a negative 1 will be 2. So I get 2 times a sub k for odd k, and 0 for even k. Right? And again, the idea, just to show that again, is if I have even k, this thing here, when it's even, becomes 1 minus 1, which is 0. Right? Because I'm raising things to a even, minus 1 to an even power will still be 1. So for an even k, this will be 0. For an odd k, I have 1 minus a minus 1, which will give me 2. So that's where this 2 comes from. So putting all that together, over here I have the same thing I saw a minute ago. So it says if I plug in my different values of k, well, when k is 0, that's even, so I get 0. So again, we get 0 for k equals 0. For k equals 1, it's now 2/3 for k equals plus or minus 1, because those are odd values. It's still 0 for k equals plus or minus 2, because that didn't change. And then I now end up with minus 1/3 for k equals plus or minus 3. Right? Well, it was minus 1/6. It's been scaled by 2. So two very different approaches for this to get from x of n to the same signal, but they get me the same Fourier series. They have to, because of the way the math works out. So another reassuring lesson from this is there's some room for creativity here. There's not one right way to find the Fourier series. And there's still another right way, which is the slow, painful way of plugging into the equation and cranking it out. But if you don't see any tricks, and sometimes there aren't any, or sometimes there's no clever way to build it out of things you know already, you just have to resort to that. And that's what the previous discrete time Fourier series example showed for. So again, if we page back one, go back to the previous page, we got the same Fourier series here, 2/3 for plus or minus 1, minus 1/3 for plus or minus 3, 0 everywhere else, and the same result here. Okay? So I have a new credit page. If people are interested, here's some more information about our university, the college, graduate studies at our university, our department, and my webpage. And again, just to summarize what we saw in the example I showed you, is a Fourier series properties example, starting from the same square wave we did in the discrete time Fourier series example on how to compute the Fourier series. I've now shown you if I manipulate properties in the k domain, what happens in the time domain I can solve directly without having to just evaluate the Fourier series sum. Or I showed another example of two different ways to find the Fourier series of a new time signal from a time signal I already knew the Fourier series for, and manipulating those properties. Well, thank you, and I'll see you again soon.